Okay, quick show of hands. Who has met, either by reading it or tutoring or whatever form, who's met this idea before? Hands straight up. Yeah, a small number? Okay, great, that's fine. Okay. For most, I'm just going to treat this as if you've never seen it before. Okay, so hopefully that would make sense. What are conics? Conics is an abbreviation. Okay, it's short for conic sections. Which then leads to the natural question, what are conic sections? Okay, if you had to guess, just off the name, what do you think a conic section is? A section of a cone is a good guess. Okay, so to put a little more detail on that, I would say it's a cross section of a cone. Okay. Now there are many different kinds of cross sections of cones, and that's what this topic is about. Okay, the idea being that you can take this shape and by slicing across it in different ways. For instance, let's just slice across it right across, right straight through it, okay? What kind of shape would you get? Well, you'd get a circle, wouldn't you? Okay. So a circle is a kind of conic section, a kind of conic, okay? Now, a circle is not the only one, there's actually a whole variety of them, and that's what this topic is about. Now, the first kind of conic section I want us to look at is actually what that little sheet was about, okay? I'm picking out the parabola because I think we're most familiar with it as it relates to conics, okay? So can we remember, well, where's the first time that you meet the parabola, like the actual shape? When's the first time you meet it? Like what grade even? Year 9? Yeah? What relevance does it have? What topic does it come under? Think back, it's a long time ago. Probably quadratics, I hope. Okay. So the idea is that the parabola is a shape. Okay. Now you might want to actually just draw yourself a small parabola because this conceptual idea is important. The parabola is a shape. Okay. So it's a piece of geometry. Okay. It's the visual representation, sorry, English people, of an algebraic idea. Does that make sense? Geometry, algebra. Here's the geometry, here's the algebra. Okay? When you've got something, when you have a polynomial and its degree is 2, so that's all algebraic talk. Okay? When you have that, you get this kind of shape when you graph the function. Okay? It has a stationary point, it has this kind of curvature, and so on and so forth. Okay? But last year, we developed it further. Okay? We noticed that, you noticed that, you can get the parabola as a shape from a totally different idea, right? Not thinking about quadratics at all. How did you consider, what way do we define the parabola? How do we define it that had nothing to do with quadratics? Do you remember? Sorry, say it again.
Parameters?
Say that one more time. Parameters. Okay, so we thought about the parametric definition. Okay. So we said, what's the standard coordinates for a parabola? For x and y, in terms of, let's call it p for parameter, what did we have out for our values? Do you remember? 2AP? AB squared, good. Okay. So you consider it as a parametric representation. Now that is different, but it's still kind of in the same vein, isn't it? Okay, like it's still the same quadratic idea, it's just sort of dressed up with another variable. Okay. We also considered it as, and I wonder if you actually got up and did this visualize, I'm not sure how you were taught it previously. We visualized it as the set of all points, or the set of points that move, if you remember that kind of definition, that are all related to a particular point and a particular line. Okay. Now we gave those two features important names. Do you remember what they were? What was the point? It was the focus, and the line was the good. Okay. So what was the relationship between the focus, the directrix, and the parabola? What was the thing that connected all of them? Good, okay, so I have no idea how well I've drawn this. Pretty badly, actually. But if I took a point, like say this one, okay, the idea is that any of these points, right, the thing that unifies all of them is that if you drew a line from there to the focus and from there to the directrix, obviously perpendicular, okay, that distance should be the same. So there's a geometric definition. What did the algebra look like? What were the coordinates? What was the name of the focus? It had a letter. It's usually S. Okay. focus, mathematicians. Anyway, S, call the directrix D. Okay, that makes sense, right? We'll call this point P with coordinates XY, right? So we would have said a locus definition, and you're probably writing this down, right? We would have said PS equals PD. Yes, this is ringing bells. Is that okay? Now, before I move and progress from there and actually give you an example, right? I just want you to notice that I can write this. This is the locus definition of the parabola. We're going to write this in a slightly different way. Okay, I'm going to get to that in a second. What's the reason why I'm starting with the parabola? Okay, because you understand it well, but also because there's something about the parabola and how it relates to, say, I told you that a circle was a conic section before, right? I could cut this in another way and I could get a parabola. Have a look at it. Have a look at the cone. What way might you cut it in order to get a parabolic kind of shape out of it? Any ideas? There's lots of different ways. Any suggestions? Any thoughts? I see a lot of you making motions with your hands. How would you articulate it verbally? What kind of cut are you going to make? What kind of slice? How is it different, for instance, to this slice? Yeah, come in. The side. Okay, let's go with that. Let's start on that, okay? Would it be parallel to the pause side? Okay, I reckon it's a good start. I think you're referring to this thing here. We have a name for this, don't we? It's actually the slant height, yes. So parallel to the slant height, I think is perfect, okay? If we, don't rub out code. If we went through it like this, okay, what kind of shape would you get? And the answer is, yes, you would get a parabola. We're slightly off, okay? Now, we're going to look at the other kinds of shapes that there are. Here's the important thing I want to get across to you. They all seem to come from this one geometric idea. Take a 3D shape, slice it to get a 2D plane across it, and then you get all these different shapes. Now, the fact that they're geometrically similar, right, what that suggests is there's some kind of, I wonder if you've caught me talking about this constantly, there's some kind of algebraic relationship between them. If there's a geometric relationship, there ought to be an algebraic one as well, okay, because they're sort of like two sides of the same coin, just looking at it from different angles. Now here's what the algebraic relationship is. I'm going to rewrite this, and it's going to be mind-blowingly complicated. Okay, watch this. Okay, step back, pause. I know that takes a while to take in, even for you guys. Okay, what have I done? All I've done is divided by this perpendicular distance. Okay, the reason it's important though is that it's drawing attention to the fact that the locus isn't just this equals that. The locus is a particular kind of ratio. Namely, the ratio between the distance to the focus, I'll just say S, and the distance to the directrix, okay? That ratio is everything, okay? That ratio is the algebraic feature that sort of binds all of these conic sections together, okay? It's so important that it gets a whole new name. It's called eccentricity. Okay. Now, being that it starts with an E, they call it E, which is a big deal. Like we just talked about it this morning, right? The E is its own special constant, and that's used all the time. It's a big deal to put two things on one letter, but there you go. Okay. So the way I would say it is the eccentricity of this parabola, actually the eccentricity of all parabolas, is 1. Okay. So that begs the question, what happens when you change the eccentricity of something? Okay, well, we're going to get to that question in due time.